another video on my channel. Today we are going to be talking about one-sided limits and how to evaluate them and to determine a few other things, and also to understand continuity and discontinuity, because those are really important in calculus and they tie very well with limits. But one more thing they also tie with is derivatives, which we'll cover in our actual calculus series. So, without further ado, let's move on to actually solving these problems. But first, we need to define what a one-sided limit is and what are limits in general. Here is a one-sided limit introduction. Now, we already went over this in one of my limit videos, so you can just skip the slide. You can go on. I'm also going to skip it, but if you want to read it and understand it more, feel free to pause the video. Let's define one-sided limits. There are two types of one-sided limits. Limit from the left side, where you have a negative as the superscript, and right side, where you have a positive as the superscript. Now, a two-sided limit exists only when both one-sided limits are equal and exist, and if they don't exist, well, they can't be equal, so that kind of makes sense. Except if it's infinity, but that's something we're going to get into later. Now, if you want to read more over it, or if you want to search on the web about it, there are a lot of academic papers out there. There's a lot of research that can be done about this, so feel free to do it if you want more. Or you can also consider subscribing and liking to this channel if you want to understand more about calculus and math in general. So, enough with the plugin, let's move on to our first example. Here's our first example. We have f of x is equal to 0 if x is less than 2, and 3 if x is greater than or equal to 2. Now we have to find the one-side limits at this, and for our final question, figure out, does the two-sided limit exist or not? So, if we look at the left-sided limit, it's coming from the left. So let's start with something that's a decent amount below 2, or 1. Now, since it's below 2, we have 1, and the value becomes 0 because that's what the piecewise function says. Now, if we have 1.9, same thing, 1.99, same thing, 1.99999 for a very long time. It's the same. And all the way up to 2, we're saying it's 0 if we had this function forever. Now, on the right side, if we start at 3, it's still 3 since it's greater than 2. If it's 2.01, it's still greater than 2, so it's 3, and so on for a very long time. So if this function continued forever, we'd have 3 as the value for x is equal to 2. So are these limits equal? Well, you tell me, do you think 0 and 3 are equal? And the answer is, sadly, no, they're not. Now, what we mean by jump discontinuity is if we have a function value at one point, and then at that same x value we have another y value, that's a jump discontinuity. And this is basically very common in piecewise functions. That's why sometimes if you have the open dots or something, you'll have to cut off the domain and range at that point and use different forms of brackets and inequalities. Now, if you ever feel like you want to work through it on your own and skip the explanation and just go straight to the answer, there's always going to be a slide down below, which I'm going to show for a few seconds. And also, that's also going to be where I'm explaining the main purpose of this question and really how common it is, because all of these questions are quite common, or at least the form of these questions. And you're probably going to see it one time or another, at least one time or another, across all the time you spend learning. Here is the answer slide. The answer slide is just showing everything, where left limit is equal to 0, right limit is equal to 3, the two-sided limit doesn't exist, and it's saying this is a classic example of jump discontinuity, where the function jumps from one value to another. Basically, where you have one x value and 2 y values. So let's move on to the next example. This example, we're going to have to use direct substitution. We have x squared plus 3 if x is less than 1, 4 if x is equal to 1, and 2x plus 2 if x is greater than 1. Now, instead of just one final question, we have two final questions. Number 1, does the two-sided limit exist? And number 2, is the function continuous at x is equal to 1? If you already figured out the answer, or you want to do it on your own and just check the answer, feel free to skip through to the answer slide. So let's start this explanation. Our first thing we're going to do is we're going to evaluate the limit from the left side. So how we write this is we have limit as x approaches 1, but instead of it being just generally, we have it from the left side, so we're going to have a negative of the function, which is f of x. This is equal to, let's just substitute 1 in here, which is basically the way you direct substitute all limits, unless you're using a table or a graph, but that's a little different, and we're not going to cover that, as it's very similar to this, and it's just reading a graph, which you should probably know from algebra. So this is equal to 1 squared plus 3. Now this is equal to 1 plus 3 or equal to 4. So if we paste this down here, the next step we have to do is evaluate this limit from the right hand side. So instead of negative, if we have positive, then if we have 2x plus 2, as it shows over here, that means we're going to have 2 times 1 plus 1, and yes, again, this is equal to 4. Now, I think you're starting to get a pattern here. Both of these values is equal to 4, and since they're equal to each other, they have the same limit value, and the two-sided limit exists, and the two-sided limit is equal to 4. How we would write this is we don't have plus or minus, we just have 1, and instead of saying 2 plus 1 is plus 1, or like 1 squared plus 3, we just say that this is equal to 4, and that's basically about it for this problem. Now, actually there's one last question which I forgot to mention. Is the function continuous at x is equal to 1? So the limits are equal, but what's important to also figure out is if the function is continuous. Now, the two-sided limits can exist, but the function can also be incontinuous. But if we look at the value that's actually at x is equal to 1, it's also 4, so it matches exactly what we were saying. So if this function is continuous and the two-sided limit also exists. Here is the answer, which it says left limit is 4, right limit is 4, two-sided limit is 4, and the function value is at 4. Now, this is basically the matching one-sided limit problem, and it shows how different approaches, if we took it from the left or right, can still yield the same image. Limit. Here is the next question, where we have trigonometric piecewise functions. Now, one note that I want to add is these functions are not close to the most complicated things, but these kind of lay the groundwork for most one-sided limit problems you're going to have, as most problems are going to deal with you calculating the two-sided limit directly. So, if we have f of x is equal to sine of x if x is less than or equal to pi over 2, and cosine of x is greater than pi over 2, we need to find the one-sided limit as x is equal to pi over 2, and we have to answer the question, does the two-sided limit exist? So let's do what we did the last problem and start by evaluating it from the left side. If we have limit as x approaches pi over 2 from the left side of f of x, this is going to be equal to sine of that same pi over 2, which is equal to 1. And if you didn't know about this, feel free to check out my trigonometry series where it covers the unit circle and the values you need to memorize for basically everything. Now, I'm not the biggest memorization fan, but some things are better to be memorized so you don't have to completely prove them, and it takes a lot less time and effort. So, this is the left side limit. Now, let's look at the right side limit. The right side limit is limit as x approaches pi over 2 from the right side of f of x, but this time is equal to cosine of pi over 2. Now, cosine of pi over 2 is equal to 0. Now, of course, if you didn't know that, you can check out my video. I told you that when I was evaluating the sine thing. So, cosine pi over 2 and sine pi over 2 basically are the exact opposites. And these limits are not equal to each other, as you can see, because 1 and 0 are not equal. So, the two-sided limit does not exist. Here is the answer, and yes, at the bottom, it shows the purpose of this function. So, this shows how functions they can have different behaviors when both component functions are continuous. What we mean by that is the limits for both sides exist, but they're not the same. So it's important to distinguish between that. Even though the limits exist, they might not be the same, and it's important to distinguish between the two of them. Now, this is a removable discontinuity. Now we have sine x over x if x is not equal to 0, and 2 if x is equal to 0. So, if we find the one-sided limits at x is equal to 0, we can do this without really having to do much algebraic substitution. If we have something like pi over 3, where it's 1 over 2 divided by pi over 3, that basically becomes closer and closer to a certain value. And if we substitute 0, it's not going to show, but it is actually 1, and we're going to actually solve this video limit in one of my later videos in this series, because this is one of the most important limits to know, and it really highlights algebraic substitution. If for those of you who are at that level and you want to know the different methods, there's algebraic substitution, and there's something called L'Hopital's rule if you ever want to look deeper into that. But yes, I will cover this in my actual calculus series. So, basically from both sides, the limit becomes 1. And does the two-sided limit exist? Yes, but is the function continuous? No, it's not, because 1 is not equal. And it shows here, left, right, two-sided limit are all 1, but the function value is 2. Now, this is an example of something we call a removable discontinuity. Basically, sometimes functions can be fixed, and they can become continuous by just merging the two limits, because if we look at this on a graph, it'd be like a single solid line, except for the fact that we have a dot in space. But since there's a line, we can just ignore that dot, and the function is continuous again. This is the last limit we're going to have. Now, we're going to consider f of x is equal to tan of x, near x is equal to pi over 2. Now, if we want to find the one-sided limit, we're going to have to evaluate tan of pi over 2 from both sides. Now, if we have x approaches pi over 2 from the left side, as we see here, of f of x, what we're going to have, this is going to be tan of pi over 2, basically, but that's two different values. So, if we have something very close to pi over 2, let's say we have pi over 4, that's going to be equal to 1. And as we keep on moving up the graph, it starts to get larger and larger and larger, and until it approaches positive infinity. Now, this is just one side of the limit, though. If we have the other limit, where we have it from the right side, let's say we have 3 pi over 4 instead of pi over 4, that that basically becomes negative cosine positive sine, so that becomes negative, but it gets greater and greater as we reach tan of pi over 2, so this becomes negative infinity for the second limit. Now, notice how I could have easily just said, okay, one of the limits doesn't exist. There's no way to make that limit exist. That means it must not have a two-sided limit. But I just showed you this for extra thoroughness and to show you that no, these are not equal and no, the limit does not exist. This is an answer, of course. This is the answer key. And this problem is really what's going to help us understand vertical asymptotes and limit formats and how limits work if they're not bounded at all. So, thank you so much. See you in the next one, and bye-bye.